our first speaker is Irene Schicker. Irene studied meteorology in Vienna and Innsbruck in Austria, and she earned her PhD in high-resolution numerical weather prediction. And her work during the past decade, among others at GeoSphere Austria, focused on AI-driven weather forecasting, on renewable energy applications, and adverse weather detection. And today, Irene will discuss the transformative role that machine learning plays in weather forecasting. Irene, the stage is yours.
Yes, thank you for the introduction, Eva, and also thank you for hosting us today. So I'm sharing my screen. I hope this works smoothly. Yeah. Good. So I'm giving you today a very brief introduction into history of weather forecasting, what happened the past more or less 3 years with machine learning, and how we can also use the tools for applications like renewable energy or extreme event detection. And as you can guess, the title pick was done using an AI model. And to start with, so defining a revolution is something like that it's fundamentally and lasting with a structural change in one or more systems, usually occurring abruptly or within a relative short period. And if we go into the history of weather forecasting and the development of weather forecast models or also climate models, that was nothing really that abruptly, nothing changing within a very short period of time. So before the 1980s, I'm not going to talk about that, what was before, but from the 80s onwards, the main innovations were that we had statistical post-processing tools, and that had already AI and other regression models. So we were already using neural networks back then, but we didn't just announce it that loudly, probably. Then we had the 3D variational data assimilation in the model. So we were assimilating observations, different altitudes, different location, time steps, and we were perturbing the initial conditions for generating ensemble members and including the uncertainty of the models of the initial conditions, the physics, into the weather forecast. But as we can see, we had a rather coarse resolution on a global scale with 150 to 200 kilometers for one grid box, and the temporal resolution in the forecast of 6 to 12 hourly. That changed in the late 90s. We had 40-bar data assimilation, we had initial conditions perturbed, we had more model physics, and we changed the resolution of the models, also the vertical resolution. From the 2000 onward, 2010 onwards, we did already work with AI-based nowcasting. We have deep learning for post-processing methods, and AI was already integrated for various data sources in the data assimilation step. Plus, the spatial resolution increased on the global scale and on the regional scale, and on the regional scale down to 1 hourly forecast frequency. In around 2020, a bit earlier, a bit later in some regions, the number of ensemble members increased from, let's say, 10 to 50 or more than 100 ensemble members of a weather forecast. We had AI-enhanced data assimilation, we have already the first purely data-driven models for forecasting. And the spatial resolution globally did increase from 10 to 25 kilometers and even down to 4 kilometers. And on the regional scale, we are now at between 1 to 3 kilometers. We have sub-hourly forecasts for the very short frequency models, and we have more than 120 vertical levels to give us the representation of the layers in the atmosphere and what's happening there. So we had already a bit of a revolution in weather forecasting with the increase of the computational resources we have. We could also increase the model resolution. But just need to change the bar. How does a classical weather model work? Just to give you an idea on how complicated it is actually. We do have tons of observations. So we have satellite data, we have buoys, we have station observations distributed all over the globe. We have ship observations, we have plane observations, we have radio sondes. So all what you can imagine in terms of observations, and in some centers also the private weather stations are fed into a weather forecasting model. We also have an ocean model, we have a surface model, and we have the static fields like topography, we have the land use, the vegetation cover, and land use and vegetation cover can vary depending on the season. So we have all these input fields. Then we have our primitive equations, and for every grid box, we have the calculations within the grid box and then the exchange between the neighboring grid boxes. We have the sub-scale processes in there, so those processes that we are not able to directly calculate with parameterizations. And what we consider in weather forecasting models in terms of processes are all the processes that you see here. And we have quite a lot of meteorological parameters in those atmospheric columns. So this is just a subset. So that's already quite a lot that is fed into a forecasting model and that needs to be calculated and transported in time forward. But lately we've seen another revolution in weather forecasting. And that happened between 2020 and 2022. There was a start of not only having purely data-driven models for for one meteorological parameter, let's say radiation forecasting or temperature forecasting with data-driven models, but we saw the emerging models with temperature, geopotential, wind speed, for instance. And that all kind of happened between 2020 and 2022. In 2022, we had the first publications, not from the meteorological community, but from companies like NVIDIA, Google, Huawei, that discovered that meteorological data are quite a lot of data, available for a very long period of time with high temporal resolution. So if you think of error 5 reanalysis data set that goes back to the 1940s, and I think it's extended backward, has an hourly resolution and a spatial resolution of 25 times 25 kilometers for one grid box. So it's already a lot of data. And they started developing data-driven prediction models, not for the very short-term forecasting, but already for a week ahead forecasting with a reduced temporal resolution. So you get forecasts for every 6 hours, but already globally with those 25 kilometers. And they performed quite well compared to the traditional models. And Mariana, I think, will give us more information on that, what ECMWF does later. But there was a huge jump from 2022 onwards, not only on a global scale, but also for regional data-driven models. And those can have a resolution of 1 to 3 kilometers. What they don't have is they don't have the full set of meteorological parameters like a meteorological model has, and a reduced vertical resolution. But still, we have this really short period of time where we have a complete change in model development and available models in our community. So what are the differences between the traditional and machine learning models? So the initial step is for both more or less the same. Based on the observations we saw before and a very short range forecast, we get this analysis field. And this is the initial field and the initial conditions for the NWP, so the numerical weather prediction model, and for the data-driven models. And then the numerical model is running on an HPC using, depending where you are, if it's global or regional, quite a lot of resources. Takes a lot of time to calculate a forecast and issues then a forecast. And for the data-driven model, that doesn't take a lot of time, as we all know. So that's the trained model. It learned from at least 40 years of reanalysis, and it runs within a couple of minutes, and you get a forecast for the next 2 weeks, roughly. And that's a huge advantage in terms of additional computational costs. So we have this ERA 5 data set, which is used for the data-driven models to train on. And that took and still takes quite a lot to calculate, because that's a weather forecasting model with a fixed version of that model, uses a set of observations, quality controlled observations, and that was calculated for the 40 years and is extended backwards to the 1940s and even earlier. And that took quite a lot of billing units for calculating. So we have here the elephant in the room, which is used to train all AI models on. And this is what a high resolution numerical weather prediction model needs for one forecasting run. So for a run, or for a model that is run 4 times a day. And in comparing, the AI model just takes 0.3 per forecast. So we still have the computational costs for the training data, but for model inference, it's way reduced in costs. Now, are they better? And I'm pretty sure Mariana will show more. The answer is also, it depends on what your scope is. But if you have a look at the 2-meter temperature results for the Northern Hemisphere, and that's the RMSE compared to observations, we have in red, we have the ECMWF high-risk model, the AIFS, and the other models are the machine learning models. And what we can see is that for the forecast for the next 10 days, the back then new version of the AIFS did outperform not only the other models, AI models, but also the AIFS model. But still, we're talking here of a global model, which with a coarse resolution and a large scale model. If we go down to local and regional scale, so let's say Austria, Switzerland, any region which is not gently sloped, let's say, or we want to see extremes, then we might need to look a bit deeper into the models and need to see how we can improve them or how applicable they are for our needs. And now a small quiz for later. I have here 6 forecasts for plus 7 days ahead. One of the forecasts is the AIFS model. All the others are machine learning models. And my question would be now, which model is the physical model? Are you able to detect the physical model simply from looking into the forecast fields? What you see here is the pressure and wind speed. So the colored regions are wind speeds. I will provide the solution at the end of the presentation, but this is questioning to the audience and also showing you what the models are capable of. But those are global models. And for the regional scale, and also thinking of extremes like we had now in Spain, like we had in Austria mid-September, they are coarse. And for some events and also for classical meteorological patterns like we have now in Vienna with the fog and the low stratus, we might need higher spatial resolution to be able to see it properly and the developments. And there are solutions already. So that's the other revolution that happened in the past, not yet 2 years. So we have Neuralio, which is also an emulator of a limited area model. So porting the idea of the global data-driven models to the local scale. The advantage of that model is that it doesn't need a lot of training data. So the initial version was programmed by a PhD student, Joel Oskarsson from Sweden, together with a colleague from the Swedish Met Service and his professor. And they had, I think, in total 4 years for training, validation, and testing of the limited area model available. So here we don't need 40 years of data. We have, I think he was using roughly 2 years of data for model training. With the latest implementation, which is available on GitHub, in case you're interested, and there's a whole community behind now, it's more or less easy to implement, but you still have to work to get the data into the model and get it trained and everything. And what you see here is that this was done by Simon Adamov from Meteo Swiss with the Swiss 1 kilometer Cosmo model as training data. This is the ground truth, and this is the prediction by the Neuralio model. And in case for those who see it or know where to look at, we do see here a small box inside. And that's because we also need, similar to the physical models, boundary conditions and a boundary zone. And this is this outer zone, and then you see this small cut here for the inner part of the model. But there also exists a so-called local zoomed AFI version, which is quite heavily developed by the Norwegian Met Office. And if I got it right, the new name for it is now BRIES, and has also the advantage that it can take a lot of different types of training data in different regions. So if you have a subset like Switzerland or Austria, Belgium, or the Danish region, you can use those data additionally to train the model for the stretched version and the zoomed version. And just to give you an idea, so this is the 9 kilometer model, the high-risk model. This is the regional model, and this is what the data-driven BRIES would give you. So we do see already a big jump between those two. Not only resolutions, but also what the added value is. But what we also see is that we still are not there from the the amplitude of the values. But the advantage is quite a lot of those models. So how can we use now all those novel weather forecasting models and also all the machine learning methods for applications, more specifically also for detection of extreme events, for weather extremes, but also applications extremes like Dunkelflaute or droughts if we look at going to the longer time scales. And we did start developing a detection method for wind speed ramping. So up ramping, down ramping with different levels of severity of the ramping. And the dots here, the gray dots, are wind turbines in Europe. And we can see that Germany has quite a lot of wind energy. And red dots are the vulnerable wind turbines. So what we detect is, will there will we have ramping happening? And are wind turbines in the regions where the wind speed ramping will happen, and is wind power production affected or not? I did the same for the mid-September flooding and storm event in Austria and the Central European countries with the regional model. And the Austrian regional model, ARUM, has a spatial resolution of 2.5 kilometers. So it's the same model and the same algorithm applied to different models without having to change anything or retrain the model. And as a side note, Boris was a stormy event besides precipitation, but did not affect that much the wind energy production. So we had quite a lot of wind energy during that event. But where can it also help? For the cutoff low detection, and some of you might have heard the name in September quite a lot. Those are those low pressure centers over the Gulf of Genoa, Adriatic Sea, that are very likely to come with a lot of precipitation or snowfall in winter. And those algorithms can also help to detect those early on and combine the detected cutoff low with different meteorological parameters to detect also the severity of events early onwards, and act as additional tool for the forecaster in that case. So they allow us to issue some severity predictions of event and support mitigation measures early onwards. But they also help us for more targeted nowcasting and prediction systems for solar irradiation, like here a thunderstorm event in Denmark, which was forecasted but not with the extent and the reduction in PV production it had. And also the local models did not really get the amount of reduction in solar irradiation for that case. And the nowcasting model would have helped on that day to for the traders, especially traders and TSO, to take some prevention measures and reduce the costs they have in trading. And this is a combination of a physics-informed neural network and a neural network that is fit for missing values. So if you have missing time steps or missing values, up to, I think, 70%, the model is still able to perform, plus the physical component that helps also getting the physical part right. And this data, so we are also using it for nowcasting in Austria, for a region in Austria in that case. And what you feed in are the last 12 time steps for predicting the next 12 time steps. And this data can be used also for as input for localized models. So we have this for PV and solar irradiation, but also for wind speed prediction and the proper prediction of extreme wind speeds with a convolutional LSTM, where we added different loss functions that are fit for imbalanced regression and a grid point-wise transformation and normalization to really enable the models to see growth and decay of such events. And as you can see here, this would be the target. And we have here now 4 models. And we can see that model 2 is not really able to get the extent, and model 3 and 4 are too high and predict too high wind speeds and a big region. And model 1 would have grasped quite good how the event really happened. So that's on, again, a field scale, but hydropower, wind power, and PV production owners and companies do want to have also really targeted predictions. And there you can use all kinds of meteorological and machine learning predictive models, feed into localized models like a foundation time series models in that case, and provide the predictions for hydropower generation at the red dot here in that region. And what you see here is the catchment for this hydropower plant. And you can do the same for PV production. And for PV production, where we also use reanalysis data combined with machine learning data, a lot of observations as well, is we generate also synthetic and semi-synthetic data to train our localized models. Then we have the numerical weather prediction models and the machine learning weather prediction models. Plus, for the nowcasting period, we add the IRAD-FIDINET satellite irradiation nowcasting, and then generate a prediction at one transformator site in Austria, using IRAD-FIDINET as extra information, and use different models for the prediction. And we can see here that the random forest did not really get it right. Plus, we can do the same for wind energy, where we can use a lookup table approach and then generate the power output for a region or a wind farm. And we can convert this either on aggregated countrywide level or for every turbine in a wind farm. So these are 37 turbines in those 2 plots. And we use machine learning quite a lot for quality control of data and for missing value imputation. So these are 3 wind farms. And here we use the clustering algorithm where we try to cluster the wind turbines into groups so that we are able to impute missing values with the neighboring or similar turbines. And another quite huge topic now is how we can support also the climate community in also building climate analysis fields like wind analysis fields, using observations and then interpolating them with machine learning to a grid of 1 times 1 kilometer, 100 times 100 meters, depending on what your aim is, and also use machine learning for downscaling of, and this is the Apolis radiation data set, which has initially 100 meters resolution, and here it was downscaled to 0.5 meter resolution. And with this information, you can either use it then for forecasting of roof PV production or for detection of roofs which are suitable for PV roof panels, or even detection of roof panels. And right now, it's more also used for downscaling the sub-seasonal to seasonal predictions. So this would be a sub-seasonal prediction with a weather course resolution. And this is what we would aim for. So we are downscaling this to the 1 kilometer resolution. But if I memorize it correctly, I think there are already some models, data-driven models, that look into predicting the sub-seasonal timescales as well. So I think there's also a lot of stuff happening right now. And we also use machine learning models for downscaling of climate scenarios, where we go from the coarse model towards the target resolution of, again, roughly 1 times 1 kilometer, or even better, depending on what we have. So there's a lot of things going on where we can also use different models. So for downscaling of climate scenarios, we could also use or think of using the AIFS model, for instance, for multivariate downscaling. And now coming to the solution, which is the physical models. Let's say, maybe I'm surprising you if you guessed right or not, and it's the upper right panel is the physical model. Thank you. Any questions, or do we have time for questions?
Thank you, Irene. Yes, we do have time for questions, and we already have one in the chat. You mentioned loss functions for imbalanced regression. Can you give a bit more detail on what exactly you are using and how does that look like?
I don't have it in the slides, but we were using the inversely weighted MSE and MAE. Plus, we were looking into the weighted MAE and weighted MSE, and we implemented the zero loss function for different quantiles. And I can post the link to the paper in the chat. I think that's easier because it's quite good described there.
Perfect, that's a good idea, thank you.
Yeah.
And after all the presentations are finished, we can talk a bit more in depth about this topic, if you want. And then from my side, or from my team, there is a question. Like, are there any limitations or problems that are not yet solved in weather forecasting, even with the help of AI? And do you think there is something, or do you think that artificial intelligence will be able to contribute to that in the future?
I think Mariana will also show a bit on that, but there are still a lot of things to be solved. So I don't think we run out of ideas. But the field is really advancing quite fast now.
Perfect. Then we just have to stay tuned. And thanks for pitching Mariana's talk. Mariana will talk about AIFS, but before she does that, here we are going to hear more on oceanographic predictions from Paraskevi Vourlioti. She's the Chief Technical Officer at Neuralio A.I, and she holds a PhD in meteorology. She also has extensive background in artificial intelligence and high-performance computing, and her current research was supported by the Vienna Scientific Cluster, concretely the VST5, and it involves using gated neural network, gated recurrent unit models, which she will talk about a bit more in her presentations. And with these models, they aim to predict maritime wave heights, and they can do so with impressive accuracy. And this work was carried out in collaboration with the private company Longroute and Paraskevi. We are looking forward to hearing more.
Hi, everyone. Thank you very much for the introduction, Eva, and very interesting talk, Irene, previously that gave a nice introduction also and a good frame for my own talk. Let me first share my screen. Sorry, I've lost the...
No problem, just take your time.
Yeah, I don't want to... Okay, perfect. I think we have now the presentation. Is it in full mode?
It is now, yes. Thank you.
Great. So thank you again for inviting us to give this talk. This work was done and backed by the EuroCC Austria and the Vienna Scientific Cluster, and it was a joint effort between Longroute and Neuralio. Longroute is a Greek company that specializes in AI-driven marine weather forecasting, and Neuralio is a company that specializes in Earth system modeling and its AI applications. And I want to talk about the oceanographic predictions and how we used HPC to train reliable AI models. But why do we even care about oceanographic predictions? So imagine here we want to go from point A to B. There is a concept of weather routing that the maritime software companies use to cut down on cost on fuels and the related emissions. Up until now, these costs have only been reduced up from 3 to 10%. So given this, there is room for AI to come and give quickly and efficiently data-driven maritime oceanographic predictions for these companies. And this is what we were what we have successfully done with Longroute. But what are the main issues here? If we delve deeper into our problem, we see that the shipping industry contributes almost 3% of the global greenhouse emissions. And already regulators want to cut down these emissions by 2050. And here is where Longroute comes and has built for these maritime software companies efficient data pipelines that have unique data sets and have in their heart some AI models to provide quickly and efficiently this data for these companies. And the current modeling framework that they are using has demonstrated even 10% better than the current state-of-the-art wave forecasting data operation that is given operationally for high wind heights. As you can imagine, all of this framework is a continuous R&D, research and development that needs to be always on the top of the cutting edge research. And where Neuralio came in and jumped along with the HPC systems is that the first model that they were using was a convolutional neural network. And this neural network is very good for 1 hour ahead forecast. And this is where we got also very good results and outperforming the operational current data given by the Copernicus Marine Store. But they are not suitable for the maritime software companies and the shipping industries. They are in need of quicker and more reliable data sets for forecast horizon beyond 1 hour. So this is where we this is the point where we collaborated. And when we were drafting our approach to solve this problem that is both scientifically but also business oriented, we saw two main categories of problems to tackle. First, we needed extensive training data sets, and here you have to remember the talk of Irene, where we said the elephant in the room, where we have the ERA5 data, the reanalysis data that are, let's say, the closest we have to the true oceanic and atmospheric states, because there is this data simulation and a constant, let's say, version of the same model that has run over many decades, so it's reliable and good quality of data. And we have to use this data and an extensive collection of it to train our model. But we need computational power. Another point was that the convolutional neural network could not give us these spatial and temporal characteristics that we needed to address to have this extended forecast horizon that I mentioned before. And to back us up in this, let's say, venture for 4 months, we went to EuroCC Austria, and they gave us access to the Vienna Scientific Cluster and to computational power, both CPU and GPU, to test and train different setups of our model, and to define a final one that we want to use in our operational services to our business industry partners. And let's see what methodology we used first to go to tackle this spatiotemporal characteristic once we had the access to the HPC and the computational power. Already we saw in the previous presentation that there are great, let's say, great progress by individual companies like Google, Huawei, that have developed models based on graph neural networks that can capture very well the spatial relationships in your field. So we already had proven work that this is a good choice, but then we had also to consider, we're talking about ocean and waves, and the complexity of it needed also a temporal aspect. Here we played around with different types of architectures, and we concluded in the gated recurrent units, and we also played around with wavelets, but in the end, gated recurrent units gave us the most stable version. And once we defined this, architecture, we imported our benchmarking code into the Vienna Scientific Cluster, and we utilized two data sources. So for the oceanographic data sets, we used the Copernicus Marine Service data that are publicly available, along with atmospheric data sets from the Copernicus data store. And the final model was a hybrid model, graph neural network with gated recurrent units to capture the spatial and temporal dependencies inside our data. And here I have to say, we are talking about training in reanalysis data from the Copernicus Marine Store and the Climate Data Store. As you can imagine, all of these data sets were in different spatial resolutions. So depending on where you go in the globe, you have different availability of reanalysis, temporal resolution, and spatial resolution. So we opted to go for the Mediterranean case because this is also why you see the Med-C name inside the data sets, because we had there high quality of data with a good spatial and temporal frequency. But of course, we knew that to predict the significant wave height, which is our target here, there are a lot of features that can affect it. And we ended selecting a number of final variables to train the model. So we had more, but we had to cut it down. In order to train it, we used a parallelization method with the task Python, and we trained with more than 500 million data points in 13 hours. And here, I have to be honest that the 13 hours comes from hyperparameter tuning, and this is the asset of being able to have computational power, because you can define the models, play around, and have the capacity to in the end take the most out of it and get the best model that you can. So we did this for the Mediterranean area, and we trained 4 models. So remember, our goal was to improve the model horizon. So we started conservatively with 6 hours forecast ahead model, 12 hours ahead model, 18 hours and 24 hours ahead. From these 4 trained models, the best and with the best performance metrics was the one that was predicting 6 hours ahead. And this is the one also that we used and for our validation. But before I go to the validation part and bother you with this, we had some challenges during the setup. We had the access in the HPC for 4 months, so we had to be very rigorous research and development loops with weekly sprints. And in the end, the major problem was not altering and tweaking the AI architecture, but handling all of the large amount of the data and the memory processing, which of course we got backup help from the technical people in the HPC. And in the end, this sounds maybe trivial, but in the end, this is what bothered us most, handling the memory, deciding the best GPU with the largest memory, cleaning efficiently our code in order to train the model without the code breaking every time. This was the greatest hurdle. And now let's go in our validation strategy. So we have saved our model. We trained the 4 models. The most stable was the 6 hours forecast ahead. So now we needed to understand what we have done. And we started first to see if generally we are capturing the circulation of the ocean. Are we doing this? And especially we're interested here because maritime software companies are interested for this, for the challenging sea conditions. So we selected challenging sea conditions and performed forecasts with our model using dates out of the training data period. So we are outside, so the model has never seen it before. And we compared this for several challenging seaway condition days and compared against both the Copernicus Marine Store forecasts that are available and satellite sea wave height. And as you can see here in the left-hand side, we have the prediction model from our side 6 hours ahead. And on the right-hand side, you see the reanalysis. And we were in general very good in capturing the general circulation, but we often saw that we had a lot of problems with the coastal areas. And here is where I want you to focus in the next slide. Sorry. Excuse me. So remember, we are facing problems in the coastal areas, and on the right-hand side here in the slide, you have in the x-axis observations, and on the y-axis predictions from our model. You can see a lump around the observations of 0.5 meters, and we are always over-predicting. And this happened whatever architecture we were testing in the Mediterranean of AI, changing all the hyperparameters, finding whatever, we had this persistent lump. Our assumption was that the model was unable to see small islands, and this means that it was building momentum. It didn't see any islands, and it attributed higher wind heights, wave heights, to our predictions. And this was the correct assumption, because on the left-hand side, you can see the same plot for the same prediction, but for the whole Mediterranean now, where the bulk disappears, which means that probably this was the reason why this was happening. And in order to have this plot, we placed a buffer zone around islands and coast of one grid point around 4 kilometers spatial resolution, and excluded it from the plot. And as you can see, although some points are under investigation and persist, we got rid of this bulk that was problematic and could not allow us to proceed with the final version of the model. But besides targeted days with challenging sea wave heights, we also explored 1 month forecasts against the reanalysis from the Copernicus Marine Store in the left, and 1 month observations by satellites, and we got small enough root mean square error, mean absolute error, and mean bias error to be confident to give it to our client. And all of this work, of course, concluded in 4 months with the help of the HPC and EuroCC Austria. And as I told you, this is a continuous R&D application that needs to be given to a final client. So we are in the next months working to deliver this. It's already operational in our premises, in a long route premises, actually, to provide this data to the software maritime company to test it and get real feedback. But on the back-end team, we are still working to develop a simulation strategy with local data and AI-enhanced data simulation to get localized improvements. And this was my talk. If you have any questions, please ask me, and I will be happy to answer.
Thank you. There is already a question in the chat, as a matter of fact. Namely, how do you handle the evaluation and testing of different models? Do you have specific pipelines in place to manage deployment strategies, especially while updating or fine-tuning the models?
The strategy was so we had different pipelines for data importing, model definition, model output. So it's more of a, let's say, configuration of how you run the model. You can, for example, we had for the different types of AI models that we tested, we had used the same data set. We performed first the hyperparameter tuning for all of them, and then we did the validation for the selected days and the metrics against the test data, and we selected the best.
Thank you.
Yeah.
Thank you. Thank you so much. And there is another question in the chat. Could you briefly explain the validation process again?
So yes, the validation process is we used our model to make 6-hour forecast to make 6-hour forecast ahead of significant wave height. We saved this forecast for days that were outside the training data set. So the training data set covered 1 year of data in 2014. I think I did not mention that. And then we found out the dates in 2022 or recent from the Copernicus Marine Store that were very challenging in the Mediterranean. So we started to see if we could capture the general trend with the model inside. Where are the high waves, where are starting the currents and how they move. This was good enough. So when we saw that we were capturing well enough, then we also compared for 1 month against reanalysis and against satellite data to calculate the root mean square error, the mean absolute error, and the mean bias error. And these are the indicators that we were small enough to give to our client. And of course, the first indicator was against the test data when we first ran the model, where you see how you are doing approximately, how well enough, but these are already inside in the first steps of model development.
Thank you so much for taking the time for answering the question in detail. A quick message from our part, Team EuroCC and Team Vienna Scientific Cluster. We are very happy that we had the opportunity to collaborate with you. Are there any concrete next steps planned in the development of your models and regarding the forecasts?
Yeah, thank you. It was also a pleasure. We got a lot of support technically and scientifically throughout our collaboration. And this has allowed us to do all the work that we did and move forward. Now, a long route is looking into data assimilation methodologies. Their AI engineer actually is looking into a method called painting. I'm not very familiar with it, but he would like to recreate with local data better routing options. And stay tuned because there is a lot of work and quick pivots, but the main operational framework is there, ready to be used by the shipping industry. Thank you.
Perfect. Thank you so much. Okay, then let's continue with Mariana Clare, who's our final speaker today. And Mariana is a researcher at the European Center for Medium Range Weather Forecasts, or ECMWF. Mariana holds a PhD in numerical and statistical techniques for uncertainty qualification in coastal ocean models from London. And she'll introduce us to an artificial intelligence forecasting system, or artificial integrated forecasting system, AIFS, who will tell us more about that. And it's a data-driven forecasting system developed at ECMWF. And so we will hear more on how AI can further weather prediction. And Mariana, thank you.
Thanks. I don't think I can. Oh yeah, now I can share my screen. Thank you for the introduction, and thank you for the invitation as well to speak here today. So you should be able to see my screen now, hopefully.
Yes, we do in full screen.
Okay. So as just mentioned, I will be talking about AIFS, which is our new data-driven probabilistic forecasting system. And obviously, it's not my own work. Sorry, it's not just my own work. So I'd like to take this opportunity to thank the huge team of people that we have working on this. And many of you will sort of recognize some of the names there. But yeah, I just want to thank them first. So Irene gave a nice introduction to how this sort of data-driven weather forecasting has sort of risen and how it's become sort of such a central topic in when we talk about weather forecasting. But I wanted to take a step back maybe and to start with, how do we actually try and train one of these machine learning models? So here I've written on the screen training for the AIFS machine learning model. But this could sort of apply for pretty much any model that you've seen, any of the data-driven weather forecasting models that you've seen. So the way it works is that we take sets of training data from ERA 5, so that's our sort of reanalysis data set, which consists of hourly states of the Earth's atmosphere since 1940. We actually only use from 1979 because that's when sort of satellite observations came in, but theoretically we could use all the way up to the 1940 period. And so each step of the training loop, we take several ERA 5 states and we take these input-output pairs. And in the training loop, we check the accuracy of our prediction against the output, which is our basic, because it's analysis, it's our best estimate of the truth at that time. And as with any sort of optimization loop, we keep on going through and through and through, correcting errors and improving accuracy until at the end we get rid of most of our red dots and we end up with lots of white dots. And this is what we call our ML model. And this it's then predicting the weather based on the physical state of the Earth after learning from ERA 5. And this is basically what most of the machine data-driven models out there are doing and what AIFS is doing. So AIFS, there was a bit of confusion at the beginning, but I think we've settled on artificial intelligence forecasting system. But yes, at one point we were integrated forecasting system as well. We followed this training scheme, which you can see on the screen here. So what we do is we take the atmospheric state at T0 and T-6, so the previous time step. We feed it into AIFS, and in the first stage of rollout, we're just trying to optimize for the first time step, which is 6-hour time steps. And so that's the stage 1. Then we do, after sort of it's been trained to a nice good state, we then try and optimize for slightly longer lead times. So what we do is we train to produce a forecast up to 72 hours ahead. So in rollout 2, we're looking at 6 hours and 12 hours. Rollout 3, 6, 12, and 18, all the way out to 72 hours. And in the deterministic setup, I saw some questions about probabilistic, so just a little highlight that probabilistic is going to be coming up. But in the deterministic setup, we train towards an area-weighted mean squared error. And this process is again fairly standard and is similar to what, for example, GraphCast did in their paper. And what does the model itself look like? Well, so this is AIFS version 0.21, which is the current version that's being sort of run in a semi-operational state. We have an encoder, which encodes the data, the physical data, onto a sort of what we would call in machine learning a latent space, but it's really just like a lower dimensional space. And you can see that it's got these bands basically around a processor. So this is the transformer blocks. And then we obviously have to decode it back into a physical space. And so the resolution of this model is 1/4 of a degree. So it's the native resolution of the ERA 5 data. And it says they're 4 times finer because the previous version of our model was only 1 degree resolution. And I'd be happy to go into a little bit more of the structure in the questions, but I just wanted to give a sort of higher level overview. And what I really wanted to show is how it's performing. How is it doing in all the metrics that we look at weather models for? So this is verification of the surface against observations, specifically 2-meter temperature. And what you can see here is the red line is IFS. So that's our global operational numerical model, and is considered one of the best models out there. So it's a really good benchmark for us to compare our AI models against. And what you can see is the previous version, when we were at 1 degree resolution, we were not doing as well as IFS. And that's sort of to be expected because we were at a coarser resolution. But when we made the change and we went to the newer version with new new model structures, new physics, but also new resolution, you can see that's the dark blue line, and that in this metric we're doing better than the numerical model, and we're also doing better than GraphCast, which previously had been seen as sort of the model to beat in the data-driven community. And we're also doing better than Pangu. And if I was to put the other AI models that people have heard of, you would also see we were doing better than them as well. one of the things that's been really highlighted and has appeared a lot in the media is about tropical cyclones and how do we, there's a lot of news in the media that AI models can do better at predicting tropical cyclones. And so we've done some analysis in-house, and we have found similar things in terms of position. So on the left, you see the position error of tropical cyclones, and you can see that the AIFS is consistently better than the HRES. So that's our operational numerical model forecast, out to long, including out to longer lead times. However, what should be highlighted, so it's completely correct that the position is better, but the intensities of the tropical cyclones are not as good in the AI models. And you can see this on the right-hand side. This is the central pressure bias, so you would want it to be sort of near zero. And you can see that the HRES, so the deterministic, the numerical model is much better than the AI model. And one of the things is resolution. We know that intensity of cyclones gets better, or tropical cyclones gets better when you have higher resolution. So we expect when we go to higher resolution, we will be able to do better as well. But it's just a sort of a caveat with all these results is that, yes, AI models do better in some aspects, but they still have some limitations in other aspects. We also look at case studies in-house as well a lot of the time. So we have this one from a windstorm which hit basically Scandinavia, windstorm Ingun. And so you can see on the left is the analysis. So this is our best guess of what actually happened. On the top right, we have the numerical forecast, and on the bottom right, we have the AIFS. And you can see that AIFS improves structure and location, but it does underestimate maximum wind speed. Which is consistent with what we found for other case studies as well. And again, I mean, IFS is at 9-kilometer resolution and AIFS is at 25-kilometer resolution. So there's some aspect which is resolution, but we can also do better, I think, for intensity. And one of the things that people mention a lot is that maybe AI models are smoothing. So because they're training towards root mean squared error, it is advantageous, especially as they get out to more uncertain conditions, to smooth out the forecast, to basically hedge their bets and go for something in the middle when they're trying to predict what's going to happen. And so here we have a nice illustration of a forecast. So on the left, we have the numerical model, and the right, we have the AI model. And you can see that especially at short lead times, it's not, the AI model is not smoothing. It's got much of the same structures and noise, if you like, as the numerical model. But it's certainly true that as we get out to longer and longer lead times, we do see smoothing relative to the IFS. And so this is where ensemble forecasting comes in. So this is sort of one of the motivations for considering ensemble forecasts rather than deterministic ones, as well as all the other motivations of quantifying uncertainty, understanding sort of the risks of certain events occurring and things like this. So as a sort of naive first guess, what you could do for ensembles would be just use the ensemble initial conditions to initialize the AI model. And this is very easy because, as Irene mentioned, the AI models are initialized with the same initial conditions as the deterministic model, as the numerical model. And so it's very easy just to initialize it with the numerical ensemble initial conditions. But what we see, which is hardly surprising, is that we have a considerable gap between spread and error. And what we want is for those dashed lines and solid lines to sort of be on top of each other, but the model is overconfident, so it doesn't have enough uncertainty in it. And this is not unexpected. This is just like an easy baseline that we need to try and beat if we're going to make progress with an AI ensemble. And so here at ECMWF, we've considered two different approaches for ensemble forecasting. So the first is, instead of using mean squared error loss, we learn an ensemble via optimizing for probabilistic scores, and specifically in this case is the CRPS, if people are familiar with it. And we also inject random noise onto the processor. And so that enables basically the model to generate its model uncertainty Basically what we do is we also have to go backwards, we also have an ensemble of initial conditions as well. So we start from the an ensemble initial conditions, we add noise, and we learn how much of that noise do we need to add to the initial conditions to optimize a probabilistic score. So that's one approach. The other approach is maybe more familiar for people who work a lot with AI models, which is to do diffusion training. So we create the forecast as a denoising task. So we start off with noise, and we basically end up with a possible realization of the truth. And we've been exploring both of these methods. And here we have some preliminary results. So we've also gone back to 1 degree resolution just because we're still in this sort of experimentation phase. And what you can see is that in these metrics, both models are doing better than AIFS. In this case, the diffusion model is maybe arguably doing slightly better, although we've seen in further tests, we've seen that maybe the CRPS method can do better as well. But it is still very much exploration. So these results change every day, but we're certainly in the right, we think we're heading in the right direction, right, given these scores. And one of the things that I mentioned was that, one of the limitations of the deterministic AI models is that they smooth at longer lead times. And here we have a metric, which is forecast activity, which you can just think of as how smooth is the forecast. And we see here, this is an experiment from the CRPS method, from the probabilistic scoring training method. You can see that the activity, so the amount of smoothness in the AIFS ensemble members and the IFS ensemble members is very, very similar. And so we're not seeing smoothing when we use these ensemble methods with these probabilistic scores. So that's a really nice result. And one of the things that this means is that we can then go out to even longer lead times, and we can go out to sub-seasonal timescales. And so this is taken from the AIFS diffusion. So it's been run out for 42 days. And where you see the blue, that means that it's improved relative, the biases are better compared to our traditional numerical model in these timescales. And the bigger the triangle, the more improvement, basically. So you can see it's very blue. Not in every variable, but in sort of the vast majority of the variables, we're seeing improvements in bias with these AI ensemble models compared to numerical models. So that's a really nice result. And there's more to come. I mean, this never stops, right, in the AI world. So we have the ambition to study how to represent full Earth system model with land, ocean, sea ice, waves, and hydrology components all within the Destiny framework. And this is a GIF that a colleague of mine provided with preliminary results for the wave direction. And you can see that it looks very, very sensible, right? You can see how the waves are propagating in this 14-day forecast, and it's already looking very impressive. It also does this, but what we do in this case is we add waves to the AIFS, and we don't see any degradation in the atmospheric variables from adding this extra variable. So that's also a really nice result. And there's definitely more to come. And then the sort of second, the other part that I wanted to highlight is, obviously at the moment we're learning from analysis, so we're not learning directly from observations. So can machine learning models do data assimilation or even replace it? And there's reasons that it can't work, as with everything. Maybe there's parts of the atmosphere that aren't directly observed, so maybe this will be really difficult. But the reason that it may work, well, current data assimilation approaches throw away significant amounts of data. We collect millions and millions of observations every day, and we can't possibly handle all of them. But an AI model could, and so maybe there's lots of information in the observations that we're not using that we could benefit from with an AI model. And so again, we have some preliminary results. So here we have, here it's actually specifically trying to predict a satellite image. So it has, on the top left, you have the input. On the bottom, you have the target, what it was trying to predict. And on the top right, you have the truth. You have the prediction. And you can see that, so where the boxes have been highlighted, it has managed to capture evolving structures. So you can see on the left-hand side that there was some sort of storm at around the southern tip of South America, and it has managed to capture how it's evolving and moving with the sort of progress of time. So it's still in very early stages, but we're definitely seeing some promising results. And then finally, I wanted to just emphasize how can you get involved, and we would really love people to be involved and to work with us and to collaborate with us. So one of the more sort of simpler methods is that actually all of our machine learning model forecasts are open to everyone on charts. So if you go on charts.ecmwf.in, you can see the forecast for coming from the AI models for up to 10 days. You can see it for total column water. You can see 2-meter temperature, 10-meter wind, all of these variables that I think are interesting for people to look at. And what I'd like to emphasize as well is we would love to look at these, spend lots of time looking at these forecasts, but we don't have that time. But if you know of an event that's happening in your region that's a really important event or something like this, which you think, I wonder how the AI models has predicted this, then we would really value sort of your feedback on this. So to tell us, yeah, actually the AIFS did really well in this event prediction, or actually it got it completely wrong when the numerical model didn't get it wrong. And that's really valuable feedback for us because we're still developing. So any sort of constructive criticism is really valuable to us. So I really encourage people to take a look at this. And then in the more sort of direct way, we have this Anemoy framework, which is all based on open source code. And the aspiration is to have a set of tools which are shared and co-developed across Europe for building data-driven forecasting systems. And yeah, sorry, I should have said Europe and beyond. And so we already have, the aim is to fill these wind turbines basically with AI models. So we already have AICON, which has come from DWD, AIFS, which is ECMWF, and I met Norway's BRIS. So we really would love people to work with us and develop and help build and use this structure. And then the final plug, I guess, is we will also be launching a global competition for the best performing AI ML models for sub-seasonal to seasonal weather predictions. So starting it in March of next year. And there's no prior expertise in weather forecasting required. So anyone who can leverage AI to improve weather predictions is very welcome. And so, yeah, this is called AI Weather Quest. And I encourage you, if you're interested, to contact my colleague, Olga, whose email is on the screen there. So with that, I'd like to conclude and thank you very much for listening, and I'm happy to take questions.
Thank you so much for the great talk. And there are a few questions in the chat. I especially liked your appeal to collaborate and contribute on a source code level. Okay, so let's look at the questions. So the first one is, global warming produces extreme weather events. Do you believe that models are accurately retrained to address this?
Yeah, so it's a really good question. So we constantly monitor when big extreme weather events come in, for example, like the flooding of the high levels of precipitation and flooding in Valencia last month. We constantly monitor whether the AI models can capture these or do capture these extreme events. And so far, we haven't seen anything that a numerical model has captured, which an AI model hasn't. But it's something that needs to be constantly monitored. And we have actually, I didn't show the slide for time, but we have a study, which hopefully I can show here, done by looking at how do AI models perform in future climates. And it's actually quite astonishing how well they do. Some of them, like Pangu weather, have very clear cold biases. So it's basically trying to revert to the previous climate state, to the climate state that it was trained on. But a lot of them are actually able to look at, to not have these cold biases. So I really encourage you to check out this work, which is on arXiv, to see how these AI models might behave in changing climates. Sorry, I've got a fly in my face.
Thank you. And the next two questions focus more on the machine learning AI side on a technical level. So the first question is, how did you combine the ensemble forecast? How did you generate a new system state with the diffusion model? It would be a conditional diffusion model, the person who asked the question assumes. And if the answer is yes, how did you condition the model?
Yeah, so it is a conditional diffusion model. So it's basically the noise is conditioned on the fields, the sort of physical fields that come in to the model. In terms of generating the ensemble, in the case of the diffusion, what we do is the diffusion model is not actually predicting forecast, it's predicting the forecast step. And so what we do is we just start with a new noise, with a new Gaussian noise, and in inference, we go from the Gaussian noise and we predict the new forecast step. And so we can do that as many times as we want, basically. And we add that forecast step onto either ensemble initial conditions coming from the numerical model or the deterministic initial conditions if we want. In the case of the CRPS probabilistic scoring method, it's the same or similar. In that case, we actually train in this ensemble setup. So we normally train with about 4 ensemble members, but then in inference, we can again do as many as we want. So we just need to start, well, we either start with ensemble initial conditions and we just propagate it through the model and we get an ensemble member, or we could start with a deterministic initial condition if we wanted. Although, yeah, I think in both cases, it's better to start with the ensemble initial conditions.
Thank you. I think the last question goes in a similar direction, but I'm going to ask it anyway. So for ensemble methods and forecast as a denoising task, is noise the sole input? Because the person who asked the question believes it should have access to observations too to predict correctly. And if so, where do you input these observations?
So not AIFS or everything that I presented, apart from that sort of looking to the future, we don't have observations. We just use it from analysis. But the way it works, let's say in this probabilistic scoring method, is that basically all the fields go through the encoder, just like they would in the deterministic. So they have, the fields like 2-meter temperature, Z500, Z850, all those fields. They all get encoded into the lower dimensional space, and the noise is only added in the lower dimensional space. And then the model works out how much noise it needs to add to these fields to make a sort of a well-calibrated ensemble forecast. So yeah, it's definitely getting information from the fields. It's not just the noise. And similarly for the diffusion model, the noise is conditioned on the fields themselves. So it has got information from the fields for sure.
Thank you so much. And another question just came in. Do you routinely check for unphysical features in your AIFS forecasts, or do you have a strategy for doing that?
Yeah, so at ECMWF, we have what we call like a daily report and a weather discussion, which is the daily report is obviously every day, and the weather discussion is every week, where we look at the forecasts. And we do this for our numerical model, and we've always done this, or well, it's dangerous to say always, but as long as I've been there and as long as I've known, we've always done these sorts of evaluations. And so what we've done is we've just sort of inserted AI models into that pipeline. So those people that look at the daily the forecast on a daily basis and report back, now look at the AI models as well. And so they will report back and they'll say this looked physical or this didn't look physical or things like that. So yeah, it's something that it's part of the sort of, I guess, the great thing about working with AI models, but in the weather service, is that we have all these people with this knowledge who can say to us, that doesn't quite look physical or like what I expected. Or they can say, oh, that looks really physical. Like the AI model's done a really good job there. So it's not something that I would say like the core development team look at. I wouldn't be able to know always if the model, well, when it goes really unphysical, then obviously everyone knows, but it's something that we work very closely with the evaluation team when they have so much expertise, right, and they've been working in this for decades, and they can tell us that looks physical, that do better, basically. Yeah.
Thank you so much. There are 2 new questions in the chat. I'm going to ask one of those and then open the plenary Q&A session. So the first one is whether your model is continuously updated and not only just monitored for correctness. And also, when you say that the model is monitored for performance, what's the measure of correctness in this scenario?
Yeah, so no, the model is not continuously updated. Like a traditional numerical model, we have cycles. Our cycles are a bit shorter than a numerical model, just because we're doing so many developments. So the last model that was sort of released was in March, I think, and we're working on the second, sort of not a second release by this stage, it's a third release in as we speak. So hopefully will be coming out soon, a third version of the model. And in terms of the monitoring, I mean, it's just a standard verification. So we look at case studies, we look at our scores, RMSE, anomaly correlation. So all this sort of standard things that you would look at in an NWP model. Also, we look at like spectra. Is it capturing small scale variability? So really, it undergoes all the very rigorous tests, I would say.
Perfect. Thank you so much. For our audience, before we conclude with our open Q&A session for all speakers, I quickly wanted to pitch an opportunity for anyone looking to deepen their skills in high-performance computing, especially for weather and climate applications, because we are organizing a one-day training together with the European Center of Excellence in Weather and Climate Simulation. And this event will take place in January. And in this course, developers can learn more about performance analysis tools to evaluate and optimize their code and fine-tune it. And during the course, you will be using the Barcelona Supercomputing Center's performance analysis tools, Extra and Paraver. And it's an ideal training for anyone involved in climate or numerical modeling. So I encourage you to check it out. Okay, and now let's get back to our speakers. We could start with the last question in the chat, which is in presentations on artificial intelligence, you often see metrics for easy parameters such as temperature. What's the current status regarding precipitation? Any one of you who has who feels like they have a feedback on that, please?
I was actually just writing an answer in the chat.
Okay.
but yeah, so yeah, it's a good question. And actually we hired somebody beginning of this year, I think he started, specifically to work on precipitation because we know it's a difficult field. So far, what we have online, what we did was we just asked the model to predict precipitation. We didn't do anything fancy or clever, and it does do really well. It sort of performs well on these sorts of precipitation-specific metrics like seeps and things like that. But as part of version 0.3, now the work of my colleague who's been working on precipitation will go into version 0.3, and we can see already that it's going to improve it again. So yeah, it's a difficult variable, but we think we're doing a good job, I think.
Thank you. Okay. And there was another question specifically for Irene from one of our participants. A question about the slides with the elephant. Can you say again what those numbers represent?
I think Mariana knows it probably even better than I. I think they are billing units.
Yeah.
Okay, thank you. Good, then let me score my questions. Okay. A question to Paraskevi. No, sorry. First, the question in the chat. What does billing units mean in this case?
These are billing units on our HPC system, Atos.
Okay.
So we have set billing units, like I think on most HPC systems. And we have discussed what's the best way to measure. I guess you should just look at the ratios, I guess, rather than the actual numbers.
Thanks. Perfect. So Paraskevi, you said you were using 2 A100 GPUs for training, and we would be interested in how you managed parallelization, and also how good the GPU utilization was during the training.
So first we worked with one, and there we had some errors with memory, as I told you before. And we started seeing how we can overcome this. First, we tried simply changing to the GPU with the largest memory. This did not work, so then we went to 2 GPUs, and then we used the Dask Python framework that uses the QPI, and the Dask splits large data sets into smaller chunks, and then the QPI comes and attributes each chunk on the GPU. And it worked, and we proceeded.
Perfect, thank you. Okay, one very interesting question in the chat. How do you see AI models forecast horizontal and temporal resolution improvement over time?
I can maybe say, I mean, I think horizontal resolution, I think we're going to follow numerical models. So we're currently at 25 kilometers. We would like to get to 9 kilometers pretty soon, which is the operational numerical model. But then we also have Destiny, which is being run globally at 4.4. So I think horizontal, yeah, we would like to improve. Temporal, I think, is a different question. I think for the moment, we'll probably stay with the 6-hour resolution. And maybe there could be, we have people actually working with us to do temporal interpolation. And I think maybe that will be more of the way forwards with temporal resolution. But I guess we're driven by what users want. So, yeah.
Thank you so much. Okay. Maximilian is asking in the chat, what's the main reason that we are not yet on a higher resolution in AI models? If there is a concrete reason that one can give.
I guess one of the reasons is memory, just like Paraskevi just discussed. Like a 9-kilometer global model into memory of GPU is not trivial, even with parallelization. And then I guess data set might cause us some issues, although we think it's probably going to be okay, especially for the 9-kilometer. So ERA 5 is this very nice, consistent data set for 40 years at 25 kilometers, 28 kilometers, depends where you are on the globe. And so, yeah, when you go to 9 kilometers, maybe you have slightly more trouble with inconsistent data set, but yeah, I would say memory on GPUs, but we're working on that.
Thank you, perfect. And so when we talk about AI models, right, there are, or it's more likely, or yeah, it can happen that there are uncertainties compared to physical models, or a higher number of uncertainty, a higher percentage of uncertainties. Do you somehow communicate this, especially to people who then work with the forecasts or hear the forecasts or see them? This is a general question directed to all speakers, so feel free to.
Yes, if I may, I think here the key word is the same framework and benchmarking. So when we develop an AI model, we want to provide the same skill scores that also we are using for the numerical weather prediction model. So someone can see how better was the AI in quantification, quantified.
Thank you. I have a question that is kind of important to me. So we all know that training, like that AI costs time and natural resources and money. And so is there a way how we can leverage artificial intelligence to even accelerate climate change mitigation and or adaptation efforts while simultaneously managing the energy consumption and the ethical challenges that we associate with AI development? And you might have some specific ideas on strategies that are needed to ensure that AI's contributions to climate action are sustainable. I'm very curious about your thoughts on that.
I think it's something that we don't think about enough, actually. I'm very guilty of it, using the big HPC systems and not thinking about how much energy I'm using to train my model. But I've been speaking to colleagues recently, and we've been sort of discussing it and talking about what we could do. I'm afraid that, yeah, I don't have an answer other than I agree that it's a problem and we should think about it.
And I have also to say this, that I'm always excited to see, I got so many GPU hours and now I can kill the planet, but it's not the way to go. But I already saw that people are working with what is so-called green code. So decide on the code that produces the less emissions in the HPC. That would be a nice, again, benchmark for different types of code to see how efficient they are and what are the results they're producing, and to choose from them that also environmental friendly.
Oh, fantastic. That sounds great. Do you have maybe more information on how these green codes work?
So I heard it in a talk. Actually, it was again a EuroCC, but now from Greece, that they delivered again a workshop on HPCs, and there were research done that people in visual code they could measure how much computational time it would need the code to be executed in the GPU, and translate it. If I was taking 10 hours to compete, in how many CO2 that would emit from the HPC center. So with a relationship, I don't know the specifics, but there is some relationship relating these two.
Okay, yeah, makes sense. Thank you so much. Okay, so there are a few new questions in the chat. I saw that one of the questions was already answered by Mariana. And there is another feedback on your answer, Mariana, if you want to look in the chat. And I will just jump to the next question, which is, in addition to forecast, short period, for example, weekly, monthly, or yearly, how is the AI application for long-term projections, for example, I don't know, 30 years or decades? Again, if you think you have an input on that, just feel free to unmute yourselves and say a few words about it.
So I was just going to say, it's not in our remit to do climate specifically, so I should highlight that it's sort of personal opinion, but I think what we think is if you have a good, stable system model, AI model, that can run out already to like a year or something like that, then why not try and do it decadal? Why not see what can happen? Climate obviously is a big question. Can they do climate? But there are already people looking into it. Like Dale Duran's group has some work where they basically did what I just described. They, not within a system model, but they took one of these data-driven models and they ran it out to long climate scales and started analyzing what it looked like. Did it look sensible? Things like that. So I think it's coming. Yeah.
Thank you. And then another question, do you think there is a way to combine loss functions that not only reduce, for example, WMSE, but can also conserve physical properties like momentum and energy?
Yeah, why not? That's beauty.
Perfect. Thank you so much. And yes? Oh.
No, actually about this question, there was a seminar recently by ECMWF and UMETSAT, I think. They had also advertised it a lot. And this was a very much discussion how to define the loss function when you're going into global and how one area affects the other in the globe. And how you tweak the loss function and then you see different results of your AI model. And if I find, I think you can watch the seminar online, and it's very nice discussions from people that are really deep into the loss function and how to set up these models for numerical weather prediction. And I'm happy to share it if you like.
Yeah, that's certainly a good idea. Thank you. Okay, another question. Is there any work on your side on nowcasting, on precipitation and cloud cover for the next few hours based on radar or satellite?
Yes, there is. So the IRAD FIDINet I showed is forecasting or nowcasting the global irradiance, but we do have models for precipitation as well, different types. So we have for radar data and combined with a numerical weather prediction model. It's a simple neural network. Then there is a foundation model and a GAN. And I think the foundation model uses also satellite data, but that's done by a colleague, so I would need to ask him. That's for precipitation, and for cloud cover, you could reverse either the global irradiance model or, because we use already the thermal infrared channels as well in the latest version, we could also try to train it on cloud cover instead of irradiance. But yes, there is work on that side.
Thank you, very interesting. A general question to all of you. Are there any trends that you are seeing in weather forecasting for the coming years? Is there anything that you can, where you say, okay, I think that's going to become more interest in the future? It will become an immediate trend. Maybe we start with you, Irene.
I'm not sure if you can call it a trend because there's so much going on, and finding or picking one trend is probably hard, but there is now ongoing work also in the Destination Earth framework on emulating the hectometric numerical weather prediction models. That's probably going to be quite interesting, and those models were specifically run for extreme events.
Mm-hmm.
So those would then be emulators for extreme event cases. Then would be the question, how do they perform under normal weather conditions? But yeah, also like for the shorter time scales or for regional scale, going more towards sub-kilometer and probably also sub-hourly resolution if we stick to the weather.
Thank you. And from these extreme weather, like we can expect more of that happening in future, right?
Yes. Yeah. So next 1.5 years probably.
Okay. Thank you. Mariana, do you have a comment on the question?
Yeah, it's a difficult question because AI moves so quickly that I don't know if there are trends. I mean, I think we will see more and more system models, sort of people looking at ocean and hydrology and sea ice and all these components and how they fit into a bigger atmospheric model. And that will enable us to go to climate scales and things like that. So I think, yeah. And maybe we'll see more and more people using observations as well and training on observations.
Thank you. Paraskevi?
Yes, and also it's a difficult question, but I also believe the transferability of the models that we build from one area to another, how they apply, or do we need always to build new models when we go and focus in different areas of the world? And there are now architectures that are well known for their transferability. But I think it's exciting. And of course, the ensemble modeling, how we can probabilistically represent our output to the end user, that is also something that the end user would like to quickly have. And ensembles are very high computational when you do it with a numerical weather prediction model or a climate model. So I think these are things that people will be actively working on. Some of the things. I think it's a disruptive area, and there are more to come.
Perfect, thank you. And then one last question before we close today's session. So we see a development in all fields of research, essentially, where that AI revolutionizes computing tasks and complements traditional supercomputing power. And I was wondering if there are any expectations in your community regarding quantum computing. Is that something that you think you can utilize in the future?
I don't think we're talking about it, at least not that I've heard. Yeah. Sorry.
No problem. It's that's completely fine. I was just wondering. Okay, perfect. If there are no other questions in the chat, then just a quick reminder that you can always get in touch with us. And there will be more webinars coming in the future. And of course, a huge thank you to all of our speakers today and to all of you who joined us today. and we hope that you leave the session with new ideas and insights regarding weather and climate forecasting.